Okay, so let's go back to this one. Proton sent into a uniform electric field. And so this time we have two plates. We're going to figure out the displacement of the electron. Not the electron, proton. Now, there's your electric field. There's your proton. So it's the problem says the proton is midway between the plates. So it comes in at exactly at the 1 centimeter point. And it's going to follow a path. So it's going to be bent off its path by the electric field. So will it actually make it all the way through? Will it hit one of the plates? And then if it makes it all the way through, what is the actual displacement? If it hits a plate, the displacement's 1 centimeter. So let's figure that out. What's one of the first things we want to figure out? We have an initial velocity. We'll set positive x and y. The first thing we want to know is how long is it between the plates? Or that's what I started with. That's one of the things you want to know. How long will it be between the plates? Okay, so remember, look up the kinematic equations. These can help you with timing and distance and acceleration. So we're going to use the kinematic equation. So again, these are things you can remember. These are things you can just look up, manipulate them, and plug in numbers. That's why you really liked them. So, so we know initially the proton's not moving in the y direction, then it is. So there's an acceleration in that direction. However, the velocity in the x direction is not affected. So the acceleration in x is 0, making that entire term 0. So if I want to figure out how long the proton is between the plates, I'm going to divide the delta x by the velocity. Okay, well, we see from the problem that's 4 centimeters. So when we solve this, what happened? Why is that one off? There it is. Our delta x will be 0.04 meters over, let's see, 8.0 times 10 to the 6 meters per second. We get a time of 5 times 10 to the negative 9 seconds that the proton will be between the plates. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . So then, well, one of the things we want to figure out is the acceleration in the y direction, because it starts not moving in that direction and then it does. So we know it has to accelerate. Okay. There's the angry martini again. So we remember that force has two representations. So it's going to be the mass of the proton times the acceleration in the y direction. What else does it equal? What is the version of force we're using now that we have charge in electric fields? Mm-hmm. Mm-hmm. Electric field. So we know that force represents each of these. And so then we can say, well, my acceleration, so what's Q going to be? Right, charge of protons. So it's just going to be that E, that base charge. And then you have the magnitude of the electric field over divided by the mass of a proton. Now, you see here, we have our magnitude of our electric field. Those other two are constants, but I want to see if this makes sense to you. So our acceleration, okay, so that is our base charge. The magnitude of our electric field, does it have to be positive or negative? It's negative because it's in the negative y direction. See, this is why, remember, this is why we set positive x and positive y. We really want to know our positive and negative directions. So that's going to be a negative. Oops, not yet. 4.55, 10 to the third. Come on. Newtons per coulomb divided by the mass of a proton. Again, some of these problems will have you looking things up quite a bit, which can get tedious, but at least you can look up the numbers. So once you calculate this, the acceleration in the y direction, negative 4.36 times 10 to the 11th meters per second squared. So let's remember that. So let's separate the two. Let's separate two reasons that acceleration can be negative. In this case, why is acceleration negative? Right. What's another case where acceleration is negative? Deceleration. So keep in mind, direction matters. It also, for example, deceleration we would usually model as something moving in the positive x direction, and deceleration's that way. So it's in the negative x direction. So so the positives and negatives really have to do with what's happening physically. Okay. No more Patrick Swayze. Okay. Well, now, one thing we can figure out is now that we have our acceleration and our time, how much is the electron actually deflected in the y direction during that time? Okay. Okay, so remember your kinematic equations, you can always rewrite them in terms of y. So they're the exact same equations, it's just x or y. So what we can say, what part of this kinematic is zero? Yeah, because it's not moving in the y direction initially. So that whole thing is zero. The delta Y is the deflection we're looking for. And so now we can take the numbers we just calculated and put them in here. Meters per second squared. Yep, squared. Don't forget the squared on there. Okay. So this will give us a negative 5.45. 10 to the negative 6 meters. What's another way you could represent that? 5.445 times 10 to the negative 6. Micrometers. So it's a negative 5.45 micrometers. Okay, so again, if you were working this problem, I would still, like, you would still get full credit if you came out with positive. You just use magnitudes, that's fine. Personally, I like positives and negatives because this tells me it's deflecting in the negative Y direction. So if it, in that amount of time, if it only deflects 5.45 micrometers, will it make it all the way through? How far does it have to deflect to hit the plate? 1 centimeter. So it doesn't even deflect a centimeter. So it makes it all the way through, and then it has a deflection of the 5.45 micrometers in the negative Y direction. Or down, you could just say down. It does make it. Because to hit a plate, it's going to have to deflect by a centimeter. It doesn't reach that. In the amount of time it's between the plates, it does not deflect a full centimeter. Okay. Torque on a dipole. I swear, I will fail you this semester. Okay. So when we're going through these, yes, I'm going to derive things. I'm going to show you where they come from. But if you haven't caught on by now, I always start with the actual theorem. This is what I start. You can use this to solve problems and plug in some numbers. So we see that the torque due to a dipole is charge times the electric field times the distance apart of the two charges, sine of theta. So let's think about this. Too bad. It is that way. So that means you're going to go a whole weekend without math because I'm not dumb enough to think that you guys are actually going to touch your homework this weekend. You're going to have homework every week. Yes. Couldn't do what? I could, I just don't want to. Nope. Because your test has nothing to do with the in-text things. The in a chapter things, yeah. So no, you need to do that for your sheets, but yeah, so the whole test will be like 30 points. So the exams have the same point weight as the homeworks. I have it set up so that you could probably like zero out two of the exams and still end up with a B or a very low A. Yep, end of chapters. A lot. I would use your homeworks as an example of what to study. Yep, Monday. Okay, you're trying to distract. Stop it. No, because of the exam. What's your question? No, possibly, or it could just be the exact same thing over again. Look, when you get to the exam, there shouldn't be a problem on there you haven't seen. Probably. The whole point of this is practice. We're trying to practice problem solving over and over and over again until you're comfortable with the process for a certain system. So remember, the first part of your exam is yeah, so it's your multiple choice, it's concepts. And then you'll have 5 questions you have to solve. So it's like 5 and 5. Because you all taught me my first year here, you hate true and false questions. It doesn't matter how I write them. It doesn't matter how I write them. You swear they're a trick question. And then I get people that do this. Really? There was. The first half were true, the second half was false. Okay. Now for torque, we have a center of rotation. That's your distance D. So let's just get ourselves a baseline here. All right. Now, if we have an electric field pointing that way, which way do the forces on each one of these point? Yeah. So positive always goes with the field. With. Negative. Negative goes the opposite direction of the field. Okay. Or so I can make, I'm going to reverse 1 and 2 so I can stay consistent with my notes and don't confuse myself. There. Now, let's start talking about what torque actually is. If you remember, torque is R. No. It's a Greek letter tall. Now, that's the cross product. That is the vector product. So this is, remember we did the dot product? That's a scalar product. It's one way to multiply vectors. It gives us a scalar number. What? Remember, you're measuring from the point of rotation. R is the distance from your point of rotation. So each R in this case is D over 2. Yes. you're going to have to do harder math. Yeah, I'd tell you. Now, this is called the cross product. This is another way to multiply vectors. This will actually give us another vector. Okay, so that's why it's called the vector product. Now, I was feeling nice today, so we're not going to go through the linear algebra derivation of the vector product, because the last time I used a matrix, everyone looked at me like, huh? It helps. It can help. So what we're going to do is, if you remember, the dot product was what trig function did the dot product use? Cosine. So this one uses sine. So that means we're going to have electric force R sine of theta. Now we have to figure out what theta is. Theta is going to be the angle that your vector makes with the rotation arm. So I can extend out that way. That's your theta, which also means that's theta. It also means that's theta. What I label? Oh, here, yeah. You could do that one too. So you just got to like, if you need to extend the arm out. This is going to be, so the arm itself, think of R as a vector. And this is the theta between the two vectors. So you can think of this as the R vector, okay? Okay, so when we're looking at the torque on this system, we have forces on both charges. So what do you think we need to do? Are we calculating how much torque do we end up having? Two? Yeah. So we're calculating the total what? Yep. So we need to calculate the total torque. I draw it my own way. I did multiple times. So the first torque is negative. The second one's positive. Why? Well, because of this. Yep. Okay, so and that's because the force E1 is negative. So that means we can say negative force E1 R sine of theta plus force E2 R sine of theta. Now again, electric force is represented how do we write it down? Yeah, the Q times E. So this is going to be negative. The Q down there has what sign on it? Negative Q. Electric field, R, use your D over 2. Sine of theta plus, top one's a positive Q times E, D over 2, sine of theta. And so if I factor out all of the terms that stay the same, I get QE E over 2, E over 2, sine theta. So the torque due to a dipole is going to be the charge times the electric field times the distance between the different charges, sine theta. Well, it's just a negative or positive charge. It's been a long week. Yeah, so I mean, yeah, vector directions can also do positive or negative, but let's stop and think for a minute. If we have, so let's draw this again. Yep. No, so I'll show you that in a second. I'll get that as close to center as possible. There's our center of rotation. So you'll find out you get the exact same thing. Yep, I need to reverse the direction of the field. Just draw the arrowhead on the field the other way. I wanted you to see this on both sides, because again, we have our E over 2, E over 2, because this time your thetas are going to be there. So really with your torque, you're looking for these acute angles. Mm-hmm. Let's see. That's a theta. Mm-hmm. Mm-hmm. So yeah, you could start putting these angles wherever they help you. And this is going to move us into Gauss's law for electric fields. So what we're going to be talking about with Gauss's law is we've already talked a little bit about Gaussian surfaces. These are surfaces that we imagine that we place in a specific symmetry, a specific spatial symmetry in order to calculate the electric field. So we're imagining the electric field fluxing through this surface. So like that's why around a point charge we put a sphere. So that's that's the symmetry of that space. Now, kind of want to take a moment here to show you the difference in like charge magnitudes. So this is a good way to come to understand charge magnitudes. You see how we have a plus Q and a minus 3Q. And magnitude wise, the 3Q is 3 times larger than the Q. So that means if you have what? 1, 2, 3, 4, 5, 6, 6 lines coming out of positive, how many lines need to be going into 3Q? So 6 lines coming out of Q. The other one is three times larger. 18. No, you don't. Because those 6 count as part of the 18. You just need to take those 6 and then go up to 18. So when you're looking at some of these diagrams, you can count the lines going in and out of different charges, and you can get an idea of their relative magnitudes. So Q will have 6 lines. Negative 3Q will have 18 field lines. Okay. So this is the basic of Gauss's law. Electric field times surface area, Q enclosed over epsilon 0. So capital Q this time because it's the total charge enclosed by the Gaussian surface. So Gauss's law is actually so we have another dot product. So that makes it EA cosine of theta. Look at the delta A. So look at the delta A. So the area element and its vector and the electric field. What is theta between those two? 0. That makes cosine of theta 1. So Gauss's law is E times A. Now, we remember our electric field is that this symmetry, what is the surface area? Surface area of a sphere. No, not 4. Not 3, 4. Go back to 4. Yep. Close. Squared. That is the surface area of a sphere. That might be, I think you might be thinking of a volume. Yep. Now we also remember that Gauss proved so if we think about the Coulomb constant being 1 over 4 pi epsilon 0, that means 1 over epsilon 0 is going to be 4 pi ke. And so what this gets us is our phi. So this is just another way to represent Gauss's law that can help you solve problems. And so then our 1 over epsilon 0, that's going to make this 4 pi KEQ. So again, you can use that to solve problems. You can use this to solve problems. And some of these Gaussian problems are a lot easier than they seem. And phi represents what? It is what through a surface. It is. So the field is doing what through the surface? It's passing through the surface, certain amount of field or in a given amount of time. That is it's the Greek letter for F. What do you think it is? It's electric flux. Gauss's law is a relation for electric flux. Now, what is the flux through one side of a cube that has a point charge of negative 2.0 microcoulombs at its center? So I've given you epsilon 0. We have a new unit here, farads per meter. Farads. F-A-R-A-D-S. I wish it was farads. Could you imagine a unit like we measured in farads? Yeah. Now, F-A-R-A-D-S. So we have our negative 2 microcoulomb charge at the center of the box. Now, the electric field put out is spherical in symmetry. So if we wanted to calculate the total flux, would we have to calculate every single side of the cube? No, we're asked to do just one side of the cube. We're getting there. 1/6. So if we weren't asked that, we'd have to do all the sides of the cube, okay? Because the field's radiating out. So okay. So again, this is a place where positive, negative becomes a little ambiguous. You could say negative, you go ahead and put the negative charge in, because if we think about that, which way is the electric field moving? It's going into the box. So you could go ahead and put the negative in. You could deal with magnitudes. If we just want to know about the flux of the field through one side, we didn't necessarily ask which way it's going. And I know some of that seems abstract. It becomes more clear as you work on it. Yeah, that's capital phi. Yep. It's the Greek letter for F. It was Greek or like
I can't read that. That looks like C.
Do what? No. Do what? No. That's actually really close. That's really, really close. Yeah. A D. Mm-hmm. Mm-hmm. I'm going to make you learn the Egyptian ABCs, which aren't even ABCs. It's 3 alphabets based on sounds. So that you'll go, I wish I had Greek again, and then you'll be happy with it. Okay, so our Q and so then we put in epsilon 0. The flux the flux that you get is going to be, you could either do negative 3.76 to represent that it's going in, that the field lines are going into the box. Okay, you have coulomb meters per farad. Let's see some other units for this. Newton meters per coulomb. voltmeters. I just want you to know that it can be that this can be all of these different units because you'll get problems in different units. Because, oh, you can start working with this. A farad is seconds to the fourth times square amps over kilograms meters squared. It also equals the coulomb per volt. So you can start playing with all these, but just know that flux has all of these units are equal. Coulomb meters per farad, Newton meters per coulomb, voltmeters. That's S. Okay. An electron. This is always a cool problem because you realize that electric and magnetic forces can actually cause levitation. An electron is suspended at a distance 1.2 centimeters above a uniform line of charge. What is the linear charge density of the line of charge? Now, this is fun. We have three different charge densities. We have volume charge density, surface charge density, linear charge density. We've already used surface charge density. What letter did we use to represent it? Surface charge density. So what do you think linear charge density is going to be? Lambda. Linear charge density. And so if surface charge density is charge per unit area, linear charge density is what? Yeah, charge per unit length. So let's take a look at what this looks like. So we'll draw a wire. We know this is just a portion of the wire. And draw my electron. Mark positive Y. Now, question. Okay, so now, what forces, so if you're drawing the free body diagram, what forces are on the electron? So if it's levitating, it's repelling that way. What else? Gravity. Minute, but it's still there. Mass of the electron times gravity. Now, if the force on the electron is pushing it up, which way does my electric field point? Nope. Pointing down. Because remember, electrons go opposite the field. So this is the free body diagram we'll use to solve this when we get back, because we're going to have to use a Gaussian surface. So question, a wire, what symmetry, what kind of Gaussian surface do you think you're going to put around a wire? What symmetry does it have? Cylinder. So we'll finish this on Monday, and then we're going to go into the next chapter pretty fast. Nope.